So let's build on this concept we introduced in the last podcast on a sloping pressure surfaces in the atmosphere and the deviation from the Taylor column, because now we are not anymore barotropic in that sense of rho being just a function of pressure or density surfaces being parallel to pressure surfaces. Going back to our geostrophy in the pressure coordinate, just get very comfortable switching back and forth. In the ocean, we don't need the pressure coordinate because we have density that can be dealt with other ways because it's incompressible. But there are places where using the density coordinate in the ocean becomes much more convenient for other reasons. Nonetheless, geostrophy in our pressure coordinate was done as gradients of height on pressure surfaces. So we had minus g over f dz dy and g over f dz dx, and we had taken away the rho into the hydrostatic balance, right? So we had mentioned this before when we looked at the zonal mean meridional sections, that when we go from the equator towards the pole, not only do temperature surfaces slope down, but the slope increases with increasing height. Okay, obviously that has to happen because the troposphere is occupying more volume in the low latitudes, warm air. Tropopause is much higher, and the entire air column is compressing and the tropopause is falling. So each surface is sloping more. Obviously, we can simply apply our geostrophy starting with zero winds at the surface, and it has to increase with height because we are still in geostrophic balance, and dz dy is greater just means u is stronger, right? So you ended up with this vertical shear, as we call it, which was fairly obvious here. Obviously here in the deep tropics we were having deep convection that was mixing up the moist potential temperature and winds and so on. So you had weak easterly winds here, but once you get off the equatorial tropical region into the subtropics, we obviously had these very strong vertical shears with the seasonality. We have to repeat this every time so that you really remember things, right? The equator to pole temperature gradient is stronger in the winter hemisphere. Energy transport required is stronger. ITCZ moves, Hadley cell moves, sinking motion moves. So you can see that this is the annual mean. There's a clear shift here and there's a clear shift back, and the same thing on this side. There are asymmetries, hemispheric asymmetries, but nonetheless winter hemisphere has stronger jet stream in both hemispheres. Right? So the main point in this context is that the winds are totally consistent with this idea that the isothermals and constant pressure surfaces are sloping more and more as you go up into the atmosphere. So atmosphere is not really barotropic, so we can derive this concept by going into the ocean. The ocean density is not constant, it's a function of temperature and salinity, but the deviations from pure water are pretty small. So you can take a reference density at some reference temperature and reference salinity, and then write a deviation as sigma, with the condition that evolves that sigma is much smaller than rho ref. Okay, remember, well, we haven't done it yet, but salinity only varies by about 30 to 35 grams per kilogram of water. So the deviation from the water density, reference density, are very small. That's all this is saying. Sigma or rho ref is much less than 1. What does that give us? We can go back to our geostrophic balance, now back in the XYZ coordinate because we are in a basically incompressible fluid, so we don't need the pressure coordinates. So minus 1 over F rho dp dy and 1 over F rho dp dx. We can look at this all the time so that you can just remember them and write them and go on with your derivation from there, especially by combining with the hydrostatic balance. Okay, so let's write dug dz and dvg dzy because we are looking for this vertical distribution of winds and trying to explain them in terms of the sloping surfaces. So that gives us g over f rho f. We have written rho as rho ref plus sigma, and remembering that this is in the denominator, we are taking the derivatives with respect to z. You end up getting minus 1 over rho squared and then rho sigma, so basically becomes g over f rho f d sigma dy and minus d sigma dx, so x direction and y direction. You notice that these expressions remain almost similar. We are just replacing z, p, and sigma, or we'll come to temperature for the atmosphere because temperature is the main ingredient for density in the atmosphere, of course compressibility as well. But we will move into pressure coordinates, so reduce it to temperature and so on. So these factors outside differ, but basically you always end up with d dy and d dx in the x and y directions respectively. Make sure you understand how we went from here to there. So if you replace rho in the denominator by just rho ref and go to this equation and write g rho ref plus sigma, and when you do dp dz you're going to replace d sigma dz from here. So sorry, d sigma dx and d sigma dy. D sigma dz is going to replace dp dz here when you take dug dz and dvg dz. I'm saying too many words, but I think you know what I mean. Okay. Simply, dug dz and dvg dz are given by g over f rho f d sigma dy minus d sigma dx. Sit down and go through the equations. It's very simple. So dug dz written in a vector form then is minus, we take the minus, g over f rho f. We have again left f outside. We are not varying f here in x and y. G hat cross grad sigma, where grad sigma is the deviation of the density, gradient of density essentially, right? Because grad rho f is going to be 0 because it's constant, right? That's the reference density. So if rho varies in the horizontal, then geostrophic current will vary in the vertical. Whoa, that's pretty amazing, right? So if you have density gradient in the horizontal and you have geostrophic balance, then the horizontal density gradient is going to produce a vertical geostrophic current variability. So horizontal density gradient is going to give you vertical geostrophic shear. Very simple. Okay, so let's do it for the atmosphere, but this time make it a function of temperature for simplicity. So in this case, rho f, it's some kind of a expansion coefficient. We had done this before, if you remember. So when you warm, density has to go down. When you cool, density has to go up. So you get this minus sign here. So rho becomes rho ref times 1 minus alpha T minus T ref. And we can just go back to our UG VG equations in terms of dp dx and dp dy, or don't go back that far, just go here and replace sigma as a function of temperature in this sense. This is actually a much better equation for ocean water. Then you get dug dz equals alpha g over f. So instead of rho ref, we have now ended up with alpha, the thermal expansion coefficient for water, our favorite z hat cross gradient of temperature. So if density is a function of temperature alone, then a horizontal gradient of temperature is going to give us vertical geostrophic shear. This is where the name thermal winds come from. Thermal winds, horizontal temperature gradient giving us vertical velocity gradients. Okay, very cool stuff, right? So this is the thermal wind, and that's where we got our vertical shear, right? So we have vertical shear. So these are the thermal winds. Okay, we have ignored obviously lots of the other terms that are important, but on the large scale, geostrophy is valid. But when geostrophy happens on a temperature gradient, we have the equator to pole temperature gradient. Then you get dug dz, which is increasing from the surface up. This is the shear we talked about, and this is the jet stream. So this is the thermal wind balance. How cool is that, right? So we haven't added too many new things. We're just sticking to a few basic large-scale balances. Geostrophy is one of them, hydrostatic balance is the other, and we are dealing with variations on these based on how density varies in the meridional direction. Obviously, meridional direction is very critical because that's the main rotational impact, right? So we have everything happening in the direction in which Coriolis varies from the equator to the poles. Very simple. At least physics-wise, you should make sure you got this completely figured out.